Hello, everyone, and welcome back. So we are on to 614, where we just talked about practicing the derivative of exponential functions, and now this is going to talk about how do you do the integral of exponential functions, because you always want to be able to do both, because those are the two main pillars of calculus. So a quick little recall before we get into some examples. So recall that what we learned is that the derivative of an exponential function, a to the x, where a is some positive number, is going to equal the natural log of that base times the function itself. And that's big. And then now, since we're going to talk about integrals, also recall what an antiderivative is. So an antiderivative function f, but they usually denote antiderivatives with capital letters, is such that when you take the derivative, of that function, of that antiderivative function f, you return to the previous function f of x. It's kind of like antiderivative is like you can think about it as it undoes the derivative. Anti, opposite, So as we get into these examples, we're going to be thinking about that. Now, the other thing to think about too that's going to help you is notice that when we take the derivative of an exponential, we get the natural log of a times ax. Now remember that natural log of a, well, that's just a constant. This is just a number. This is saying e to what power is going to give me a. So this is just a number. All right, so it's a stretch factor, if you might call it. Okay. So think about example 1 here. What's the integral of 2 to the x dx? Well, if we were to think backwards and say, okay, we want an antiderivative function, because that's what integral means, is we want an antiderivative function such that when you take the derivative of it, we're going to return back to 2 to the x. So when I take the derivative of these functions, I add on a stretch factor. I multiply by a constant. Well, because we have to undo that, instead of multiplying by that constant, we have to divide by that constant. So when we do the integral of 2 to the x, we have to account for the idea that when we do the derivative to check our answer, well, we have to undo that stretch factor by now dividing. And then what's great about exponentials is that it always is the function itself. So then times 2 to the x. And don't forget that since it's an open integral, we do plus c to account for all vertical movement. So that's what we think the answer is. Now let's check. And I highly recommend you check all your answers on this. So we check this function because we can take the derivative of this antiderivative to check if we return back to the original function. Does this function, 1 over natural log of 2 times 2 to the x plus c, is that going to equal 2 to the x? That's what we're asking ourselves. Okay. So remember that the derivative of a constant doesn't matter. You can even pull that out in front if you wanted to. So you could write 1 over natural log of 2 times d dx of 2 to the x plus c. That's totally acceptable. So the derivative of 2 to the x, so we have 1 over natural log of 2 times the derivative of 2 to the x is going to be natural log of 2 times 2 to the x. And then the derivative of c is 0, so that's, plus 0, which I put that there to show you, but you don't need to write it. Now what's great is notice the idea that when we took the derivative of 2 to the x, we added on a stretch factor, a constant, natural log of 2. But we accounted for that with the antiderivative by dividing by that, which those go away, so we just get 2 to the x, which is exactly what we were hoping to get. So this right here is your answer for that. Okay. Example 2, we have 5 times 3x. Now don't be thrown off by that 5. Remember that you can, with constants in front, stretch factors, you can always bring that in front. So that's equivalent, if that 5 bothers you, of doing 5 and then do the integral of 3 to the x dx. Now, we have to account for that when we take the derivative of its antiderivative. Because remember, with integrals, we're finding an antiderivative function. So we have to account for that by saying we're going to divide by that constant, natural log of 3, and then it's times the function itself. And then we add plus c for the open integral. Right? Let's check this. So is the derivative of, and I'm going to combine these two and just write as 5 over natural log of 3 times 3 to the x, is this going to equal our original function? So if we check the derivative here, that is just a constant, won't affect it, so that just stays where it's at, times the derivative of 3 to the x, which is natural log of 3 times 3 to the x, and then derivative of c is 0. These will cancel out, so we're left with 5 times 3 to the x, which, voila, that is the original function. So the derivative of the antiderivative that we think the answer is the original function itself. Good. And then example 3, natural log of 5 dx. Now don't be thrown off. Again, natural log of 5 is just a constant. That's just a number. So it doesn't affect the integral here. And you can always pull it out in front like we did with the 5. That helps you feel more comfortable with the calculations. Now I'm not going to here. I'm just going to include it. And then e to the x, well, we could account for that by doing 1 over natural log of e. But we don't need that because that's just going to become 1. But I'll put it there for purposes of visual. And then if we simplify that, we're going to get natural log of 5. This whole thing is just going to go to 1. So just natural log of 5 e to the x plus c. And if we check this to make sure we did it right, the derivative of natural log of 5 e to the x plus c, well, that's going to give us natural log of 5 times the derivative of e to the x, which is just e to the x itself, and then plus c is nothing, which is the original function f, so we are good to go. So that's doing integrals of exponential functions. Think about the idea that, remember, an antiderivative is a function that when you take the derivative, it undoes it. So you just have to account for that constant that derivatives create on exponentials. Now, example 4 and 5 is putting it all together. I want to show you these a little bit more extended problems that use everything we've learned up until this point. So what's the derivative of 4 to the power of cosine e to the power of 2x? So there's going to be a lot of chain rule here. I hope you're ready. First, we have an exponential, so it's the natural log of the base times the function itself. And then because of chain rule, we left the inside alone, so now we have to take the derivative of this. And the derivative of cosine e to the 2x, well, that's chain rule itself, where it's the derivative of the outside, which is negative sign, leaving the inside alone, times the derivative of the inside. And now we're looking at the derivative of e to the 2x, which the derivative of e to the 2x is e to the 2x. I didn't put the natural log because it's e, but then because of chain rule, we take the derivative of the 2x, which is then 2. So there's a lot of chain rules there. Simplifying this, your only constants here are 2 and natural log 4. So I might write 2 natural log 4, and everything else, the order is not as big a deal because they're all functions in terms of x. Put the negative in front from the sign there. And that messy function is the derivative of that first function. A little bit more complicated than what that looks like. Hey, but pretty cool. That function tells us its rate of change at any moment. All right, in example 5, the derivative of e to the x cosecant 2 to the x. All right, we're going to have to use product rule here. So the first times the derivative of the second, and the derivative of cosecant is negative cosecant, the function, cotangent, the inside. But then when we did the derivative here, it's the derivative of the outside, leaving the inside alone. That's why I left it to the x, times the derivative of the inside, and the derivative of 2 to the x is natural log of 2 times 2 to the x. Good. So all of that is the derivative of cosecant 2 to the x. And then it's the derivative of the first, or the first times the derivative of the second, plus the second times the derivative of the first, which, whew, thank goodness, it's just e to the x. And there is your answer. If I was to clean this up a little bit, put our constants out in front. The only one there is natural log of 2. Put the negative in front, and everything else will just follow. And over here, plus, I'm just going to put the e to the x in front. Not that it matters. And there it is. So that's exponential functions, derivatives and integrals, and even adding in product rule and chain rule. So you can see that. Hope that makes sense to you. If not, please reach out to me and I can help a little bit more with you. All right. Good luck. Bye-bye.